All right, folks, here's a recap of Chapter 2, Lesson 4, our first introduction to geometric proofs. First thing you do is you read the conjecture. The way you read the conjecture is if y is the midpoint of xz and xy is congruent to wy, then wy is congruent to yz. Next thing you do is convince yourself the conjecture is correct by marking up the diagram. Y is the midpoint of xz. If y is the midpoint of xz, what do we immediately know? We know that xy is congruent to yz. Secondly, we're told that xy is congruent to wy. xy is congruent to wy, so you mark that. Since xy had a single tick, wy is a single tick. Now, what are we trying to prove? We're trying to prove that wy is congruent to yz. Do we believe that? Absolutely. wy is congruent to yz. No problems. All right. Now we go ahead and do the proof. Where do we start? Y is the midpoint of xz. Why? Because it's given. Any questions? No? All right. What flows naturally out of y is the midpoint of xz? Y is the midpoint of xz? Well, we know it's that xy is congruent to yz. xy is congruent to yz. What's your reason? Midpoint theorem. All right. Now we need to pause and realize we're taking something called the congruence approach. There's two languages you can primarily write in proofs. One language is congruence, the other one's equality. Congruence language uses this congruence symbol, okay? And it's kind of that ancient Greek writing style. And then obviously equality approach uses equal signs. You notice there's no equal signs in the proof we're about to do here, because we're taking a congruence approach. It's like we're writing in the style of the ancient Greeks. All right. Whenever you use the midpoint to divide a segment into two smaller segments that are congruent, that's called the midpoint theorem in the congruence approach language. It's called something different in inequalities. All right, what are we going to do in line 3? Well, we just go grab our next given, which is that xy is congruent to wy. Write that in, and it's given. Well, we know at this point the proof should be done, and it pretty much is. Here's what we do. I want you to look at lines 2 and lines 3. Can you stare at 2 and 3? What do you notice? xy is congruent to yz, and xy is congruent to wy. From that, what naturally flows out of that? Yeah, we're like, well, xy is here in both locations. Therefore, yz and wy must be congruent. Wy must be congruent to yz, which is great. That's where you want to go. But you can't actually do that in the congruence language. It doesn't exist. Substitution does not exist. This would be a great case of substitution, right? xy equals yz, xy equals wy, therefore wy equals yz, wy equals yz, boom, done. Like, you'd be done. Wy equals yz. But you can't. Listen to me, substitution does not exist in the ancient Greek mind. Instead, they had a property called the transitive property of congruence, which is more beautiful, less utilitarian. Here's the congruence property of the transitive property of congruence. If A is congruent to B and B is congruent to C, then A is congruent to C. Let me say it again. If dog is congruent to cat and cat is congruent to mouse, then dog is congruent to mouse. Always follows that same pattern. Da 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 da. And it can only follow that pattern exactly. So we can't say, since xy is congruent to yz and xy is congruent to wy, that wy is congruent to yz straight out, because that wouldn't fit the pattern. Instead, what we have to do is flip 3 from xy is congruent to wy to wy is congruent to xy. You'll see the pattern in a second. What causes you to be able to flip this? You'd say, well, it's pretty obvious. Yeah, it is obvious. What allows you to flip it is it putting you at a line of symmetry right here. When you flipped over the line of symmetry, that's what allows you to flip it. And it's called, coincidentally, the symmetric property of congruence. Okay. So all we did was flip line 3 from xy is congruent to wy is congruent to xy. You're like, why? Why are we doing this again? Okay, let me highlight some stuff for you here. Let's highlight lines 2 and lines 4. And let's read line 4 first. Here we go, watch. wy is congruent to xy. xy is congruent to yz. Therefore, wy is congruent to yz. Transitive property of congruence. And then you cite the lines. It says lines 4 and 2. Again, Ba-ba-da-ba-da, ska-ba-da-ba-da, ba-ba-da-ba-da. WY is congruent to XY. XY is congruent to YZ. Therefore, WY is congruent to YZ. It's called the transitive property of congruence. It's the only type of substitution you can do. It's got to be pretty. You're like, why? Because math cults in the ancient world were about beauty. Beauty was important to them. Like, what's more important to you, being utilitarian, just getting the job done, or being beautiful? Well, you're probably going to say, just want to get it done, utilitarian approach. Great. Then you're going to love the equity approach, the equality approach, because that allows for substitution. It's not pretty, but it gets the job done. It gets done fast. The ancient Greeks, they wanted their quote unquote substitution to be prettier, to be a da 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 da. Now, you may say that seems silly. Okay, but would you rather be beautiful or ugly? Oh, you'd rather be beautiful? Fantastic. So you do understand the importance of beauty on some level. All right, let's finish up this proof. Oh, we already have. We're done. Look, we want to prove WY is congruent to YZ, and we have. Done. 5 lines. Let's do exactly the same proof now, exactly the same proof, the same one, but now we'll use an equality approach. Equality is another word for equation. It's got an equal sign in it, right? Equality approach. Well, what are we going to write as the first line? Just like before, y is the midpoint of xz given. What's going to flow naturally out of y being the midpoint of xz, y being the midpoint of xz? You know that x, y, and yz are congruent. But since we're taking an equality approach, instead of talking about congruence, we'll talk about their measures are equal. So we say xy is equal to yz. Xy is equal to yz. They have equal measures. So no bar on the top, right? And it's an equality, an equation. Now you're like, okay, well then it must be the midpoint theorem. Except in this language, in modern parlance, we don't say the midpoint theorem, we say the definition of midpoint. Like, why can't we just call it all the same stuff? Why can't we just call it the midpoint theorem? Well, it's 2 different languages. I just want you to understand. I know, like, it's the same concept, but you're speaking different language and you're translating between them. Like when we're writing algebra, we don't switch into geometry midstream. It would be weird. If we're talking in English, we don't just start talking in other languages randomly. It would be weird, wouldn't it? If I was like, okay, class, hello, this is geometry. Je m'appelle Vincent Cartenuto. Il y a beaucoup de choses à faire aujourd'hui. Man, today we're looking about, we're learning about multiplication. Sie ist das Gegenteil von schmutzig. Multiplication. Oh, that's division, of course, right? It would be weird if I just started speaking French and German while speaking English. Same thing here. You got to respect the ancient language, the congruence language, and the modern parlance equality. And you have to translate between the two. All right, good. Let's go on to line 3. You're just going to take this same given, xy is congruent to wy, given. But now it's in congruence language. Can you see it's got a congruency symbol? What language do we want to be in? Equality. So somehow I have to go from congruence to equation. XY is congruent to WY becomes XY equals WY. Instead of the segments being the same, we say the measures of the segments are equal. It means the same thing. 2 different languages. Like this is French, this is German. So the question is, what allows us to translate between the 2 languages? It's always this thing, the definition of congruence. Definition of congruence. We're like, well, why is that what allows us to translate between old Greek congruence language and modern equality language? Because it's how we define congruence. If you try to tell a modern person what it means to say that 2 segments are congruent, you say, oh, it means they have equal measure. See, it's right there in our definition of what the ancient Greeks meant by congruence. Okay, so the definition of congruence is like the Rosetta Stone. Do you know what the Rosetta Stone is? It was a stone that was found in the past 100 years. It's found. It's in the British Museum, and it had 2 ancient writing styles on it. One is ancient Greek, and one is Egyptian hieroglyphics. We didn't know how to speak Egyptian hieroglyphics, but because we had the parallel text, now we can figure out how to speak Egyptian hieroglyphics or read them or read them, right? So the Rosetta Stone is what allows you to translate between languages. And so that's what our definition of congruence is. This is our Rosetta Stone in both directions, going from equality to congruence and congruence to equality. All right. Well, Good news, you can use substitution in equalities and equations. You've been doing it for a long time, right? So you don't doesn't have to be pretty. You don't need the transitive property or anything like that. You just, hey, look, if it works, it works. XY is equal to YZ, great. XY is equal to WY, boom. So what do we immediately know? WY and YZ are equal. That's line 5. WY is equal to YZ. What's the property? Substitution, or substitution property of equality is the longer way to say it. Lines 2 and 4. You always have to cite, whenever you use substitution, you have to cite, or transitive property, you have to cite the lines. You don't have to cite all this other stuff here, but line 2 and line 4 for substitution, you have to do that. Okay? Lastly, we have to prove exactly what we said we're going to prove. So it looks like the proof's over, right? We're done. We got WY is equal to YZ, which is the same as WY is congruent to YZ. But it's not exactly the same. We have to end the proof in the same language it was written in, and it was written in congruence. So we have to convert back from WY equals YZ, the equality approach, into WY is congruent to YZ, the congruence approach. What's the Rosetta Stone that allows us to translate? The definition of congruence. All right. Take a breather. Let's move on. That's about 5 minutes worth. Okay. Another new proof here. Now we got C as the midpoint of AB. Flows naturally out of C as the midpoint of AB. Well, you know, AC is congruent to CB. We're taking a congruence approach again, people. All right. B is the midpoint of CD. Well, you know, if B is the midpoint of CD, that CB must be congruent to BD. Since CB is a single tick, so does BD. All right, what are we trying to prove here? We're trying to prove that AC is congruent to BD. Do we believe it? AC is congruent to BD? Absolutely. This is going to work. No problems. So let's run it. First line, C is the midpoint of AB, given. We're taking a congruence approach, so what do we say? We say naturally what flows out of line 1 into line 2, AC is congruent to CB. See it? In this language, we use midpoint theorem as the reason. All right, go to your next given. B is the midpoint of CD. B is the midpoint of CD right here. Line 3, what flows naturally out of that? CB is congruent to BD. Boom, midpoint theorem. All right, now we're in congruence land. You may not use substitution. You can only use the transitive property of congruence. It has to be all pretty like. But good news, let me highlight these for you. If I highlight line 2, boom, and I highlight line 4, oh, look at this. It's already pretty. It just happened to land that way. AC is congruent to CB. CB is congruent to BD. Therefore, AC is congruent to BD. AC is congruent to BD. Once again, da 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 da. Beautiful. Makes the cultists happy. Anyway, there we go. So AC is congruent to BD. Transitive property of congruence. Make sure you cite the lines 2 and 4. Kind of getting it? That's the congruence approach. Notice there are no equations in here at all. It's all congruence language. All right, let's try the same proof. This time, same exact proof, but we're going to use the equality approach. Equality approach, right? So we're going to have a bunch of equations. We've got to translate. Start the same way you started before. C is the midpoint of AB. Boom. What flows naturally out of C is the midpoint of AB. AC, the length AC is equal to the length CB. So measure of AC is equal to the measure of CB. Definition of a midpoint. I thought we call it a midpoint theorem. Only for congruence, in modern parlance, in equality, you call it the definition of midpoint. You're like, again, why? Because they're different languages, and it's just weird to constantly be speaking in different languages at the same time. You got to keep your languages straight. Respect the languages. All right, next. Another given. B is the midpoint of CD. What flows naturally out of that? CB is equal to BD. Boom. Definition of midpoint. All right. Now, no problem. Let's just highlight 2 and 4 again and look at them. See what it says. It says AC is equal to CB, and we have CB is equal to BD. So you know that AC is going to equal BD. AC equals BD. Now, you can write this in one of 2 ways. That is clearly the transitive property. It's pretty. AC equals CB, CB equals BD, therefore AC equals BD. It worked out perfectly, just like it did for congruence. So it's the transitive property of equality, lines 2 and 4. What else could you have called this instead of the transitive property of equality? You could have called it the substitution property of equality, or substitution. Why? Because substitution works, right? AC equals CB, CB equals BD. Therefore, yeah, AC equals BD. Substitution is like a much broader, much more utilitarian system. So either transit property equality or substitution you could have written for equality. And then just make sure you convert back. You have to prove exactly this. Segment AC is congruent to segment BD. How are you going to get to segment AD is congruent to BD? You convert from equality to congruence language using our Rosetta Stone definition of congruence. Again, you don't have to write line 5, line 3, line 1. You do have to write for transitive property or for substitution lines 2 and 4. All right, look at the next slide. It's the same proof again, but this time I wrote it with substitution property of equality. So I just wanted to show you that's another equality approach. You can always use substitution with equalities. And if you're utilitarian, you don't care about being all pretty like, if you're doing an equality approach, you could always use substitution. It's great. Okay. Substitution property is like a Brooklyn guy. Being like, hey, you and you and you and you's over there. You're all the same, right? So you're all equal. Boom. Like there's no beauty in it, but it works very effectively. Good. One more proof and we'll be done. B is the midpoint of AC. Okay, B is the midpoint of AC. So I mark this sucker up. Sorry, let me just get this mark. Okay. AB is going to be equal. We're taking an equality approach now, right? Looks like an equality approach. BC. E is the midpoint of DF. E is the midpoint of DF means that DE is going to be equal to EF. Well then, oh, there's some more information here. We're told that AB is congruent to DE. Okay, so now we know that AB is congruent to DE. Guess what I should have done is like a single tick here and a single tick here, a double tick here and a double tick here, because I don't know that those be congruent. But once I know that AB is congruent to DE, then I know they're both single ticks, then all 4 of these are single ticks. Therefore, what I need to prove is there, BC is congruent to EF. I just didn't want to erase because I don't see the eraser. Oh, there's the eraser. Here, I'll do it one more time for you can see, okay? I didn't see the eraser earlier. Good. So B is the midpoint of AC. AB equals BC. Now we have E is the midpoint of DF. So DE is congruent to EF, yes? Double ticks. But then we see in line 3, AB is congruent to DE. So if AB is also congruent to DE, then they should have the same number of ticks. So this is actually a single tick situation. So I come on my eraser and I'm like, okay, this is a single tick. But if that's a single tick, then this is a single tick because we already said they're congruent. Now you see the conclusion, don't you? Which is that BC is congruent to EF. You see it. We move on to the proof. You know what the first line is to be. B is the midpoint of AC given. You know what flows out of that. AB is equal to BC. Remember, we're taking the equality approach. Definition of midpoint. Second given. E is the midpoint of DF. E is the midpoint of DF means DE is equal to EF. E is the midpoint of DF. DE equal to EF. Definition of midpoint. All right. Now what are we going to do? Oh man, there's a third given. You see there's 8 lines here? Why? Because it's a third given. What's the third given? AB is congruent to DE. You got to write the givens as they are. So for line 5, AB is congruent to DE. A is congruent to DE. What's your reason? Given. It's a third given. But hey, we're taking an equality approach, right? So we don't want to be in this ancient language. We got to convert to modern parlance. AB equals DE. What's the Rosetta Stone that allows us to do that? Definition of congruence. Do you see that? Great. Now, using an equality approach, good news, you get to use substitution. So what 3 lines are you going to use here with your substitution? And the answer is lines 2, line 4, and line 6. Like, why 3 lines this time? You'll see. Do you see that? First of all, they're the only 3 lines that have equations, that are equalities, that have equal signs. Everything else doesn't have equal signs. So that gives it a hint. Now, AB equals BC, DE equals EF, AB equals DE. That doesn't look related at all. I'm all so confused right now. Oh, wait a second. Look over here. AB. Oh, AB is equal to BC, so this is really BC. DE. Oh, DE is really EF. So this is really EF. Okay, so AB is really BC, and DE is really EF. So this is BC equals EF. That's where BC equals EF comes from. Substitution is your reason. Lines 2, 4, and 6. With the transitive property from congruence, you can never have like 3 lines. You only have 2. It's ba da ba da da ba da ba da da ba da da. Substitution, it's like broken. Hey, you all is like equal, so you all the same. Boom, done. There it is. BC equals EF. And you're like, well, why particularly did you choose BC equals EF? There's a whole bunch of combinations that are equal here, a bunch of equal things. Because where am I headed in this proof? To BC is congruent to EF. Look ahead to where what I need to prove. So I need BC equals EF. And now I have to end with BC is congruent to EF because that's how it's written in the proof. To get there, I've got to translate back from modern equality to ancient congruence statement using my Rosetta Stone definition of congruence. All right, hopefully that made it crystal clear to you what's going on. Have a good night.